Hi everyone, thanks for checking out this video. So this is going to be the fourth video in this series I'm making on how to make neural networks from scratch in Julia. And if you guys have been watching this series so far, hopefully you'll remember that in the last video we were able to implement the forward pass of the addition operation. So now we can do value plus value operations going forward. But now the challenge for this video, and probably also the next video, because I think I'm going to split this up into two parts, is we want to be able to do the backpropagation for addition, meaning the backward pass, where we go back and calculate the derivatives of the output with respect to the inputs. So yeah, that's going to be the goal for probably the next two videos, because yeah, this part is a little bit complicated, at least compared to what we've done so far, although it's not that difficult. And really this part, the backward pass, this is like the most difficult thing that we're going to do in this whole video series. So if you guys make it through this video and the next video, then everything should be kind of downhill from there. But yeah, this part is, it's both difficult and also probably the most important part, because this concept of backpropagation is what allows neural networks to actually work. That's how kind of the magic of them actually happens. It's all about calculating the derivative of the loss with respect to the parameters so that you can update the parameters accordingly. And I know I keep repeating that, but yeah, it is very important. So yeah, this video and the next video are probably going to be the most difficult parts of this series and also the most important parts. So if you guys just make it through this video and the next video, then it should be pretty easy from there, I think. But yeah, let's get into it. So this is the code that we have so far. Hopefully you guys have been watching the previous videos in the series. But yeah, this is all that we've written so far. So this allows us to define values, and part of that is our operation object. We have our value constructor. This just lets us print them out, compare if they're the same, and then add them together in the forward pass. Okay, so now we want to be able to do the backward pass. So before we start writing the code for this, I'm just going to show you guys like what we want to be able to do at the end of this video and the next video. I'm going to show you guys what code we should be able to run and have it work by the time we're done with this backward pass implementation. So we want to be able to say x equals value 2, y equals value 3, z equals x plus y, and up until this point, we should be good. We've already written the code for this forward pass of addition. But what we want to be able to do when we're done with the backward pass is be able to call backward z, and then have it automatically calculate the gradients of x and y. And when I say gradient, I mean the derivative of z with respect to x and the derivative of z with respect to y. And those derivatives are stored in x.grad and y.grad. So this should be dz dx, which is 1, just because if you guys are a little bit rusty on the calculus, that's just what the derivative is for this kind of addition that we're doing. The intuitive explanation for that is that if we increase x by 1, then z will also increase by 1. And then same thing for y.grad. We want this to also be 1. Whoops, should be a comment, sorry. Yeah, so if we try to run this now, of course, it's just got to give an error because this backward isn't defined. So the goal is over this video and the next video to write the code so that we can actually run this and have it work. Okay, so I'm gonna for now like leave this kind of at the end, and then we're gonna work on writing the code to like get up to this point. So I'll actually just comment this out for now. Okay, so let's talk about how we're actually going to do this. So there's two things we need. one of these things we're going to have to write is this backward function. So this backward function is going to be the user-facing function that the user calls on their last variable when they're ready to calculate the derivative of that last variable with respect to all of the input variables that went into it. So I'll say user-facing function performs full backward pass. And when I'm saying full backward pass, part of what I mean there is we could have had more operations than just one addition operation. We could have had a whole chain of operations. So we could have said like W equals X plus Y, Z equals A plus B, and then C equals W plus Z. And then we should be able to call backward C on our final output here, and then get all of the derivatives of C with respect to all of the original input variables, X, Y, A, and B. So that's what I mean when I say full backward pass, is it could be a whole chain of operations where we're going all the way back through the chain. So that's what I mean when I say full backward pass. Maybe I'll just but before we do that, so that's going to be the actual user-facing backward pass function that the user is going to call whenever they're ready. But we're also going to have an internal function that the user doesn't actually call, but that does the work of the backward pass internally. So this is going to be called backprop ! And whoops, sorry guys. Backprop. And so this is going to be what does the actual backward pass for one operation. So this is going to be what does the backward pass for like each one of these individual addition operations. So internally, this is going to be calling backprop C, backprop W, backprop Z, and then so that's going to take care of all of the actual derivative calculations for X, Y, A, and B. And this is also going to call it for A, B, X, and Y too. Although for those it's not going to do anything, because basically the way this backprop function will work is when it's calling backprop C, that's calculating the derivative of C with respect to W and Z. And then when it calls backprop W, that's basically calculating the derivative with respect to the operands of W, which is X and Y. So when we do this full backward pass, it's going to be calling this internal backprop function a bunch of times, basically on every variable that we have to calculate, to update the gradients of the operands of that variable. And when we get to the end, like what we could call like the leaf nodes here, it's going to be called on these two. But since these ones like X and Y don't have any operands, they're like the leaf operands, I guess we'd call them. Then this will just do nothing. Okay, so now we're going to actually start writing first of all this internal backprop function, and I think that'll be the focus of this video. And then in the next video we'll do this full backward pass function. Maybe I'll just leave a comment here too. Internal function called on each variable to update the gradients of the operands for that variable. And yeah, again, if any of this is like seeming confusing to you guys, hopefully it'll just make more sense when we actually try it out and like do like an example with it. Okay, so let's get started with trying to write this backprop function here. So the way we're going to do this internal backprop function is we're going to be taking advantage of something cool about Julia programming, which is this thing called multiple dispatch. So this is basically what what you kind of do in Julia, like rather than traditional object-oriented programming. So what multiple dispatch means is basically that you can use the same function name multiple times, but instruct it to do different things based on what kind of type the input is. So if you guys remember from before, our value objects are actually storing this like type parameter that tells us about what operation was used to create the value. And the simplest case is when we have one of these like leaf nodes here that was just not created from an operation but was defined by the user. So if we say like x equals value 3, for example, if we then print out the type of x, we see its value with type parameter nothing. So this nothing here just means that x wasn't created from an operation. It was just defined by the user. So this is going to be the easiest case to start with for backprop, is that we're actually just going to say for the backprop for these like leaf node cases, we're going to say backprop val type value with type parameter nothing equals nothing. So this is like a formality, basically just telling the backprop function, okay, if the input is a value of type parameter nothing, meaning a value that was just defined by the user, not created from an operation, just do nothing. So this is just kind of a formality, because the goal of backprop is to update the gradients of the operands, and these ones of type nothing don't have any operands. They weren't created from an operation, so there's no gradients that need to be updated. That's kind of the simple case. The next case is we want to be able to define backprop for a value that was created from an addition operation. So for this, I'm going to give you guys a little bit of complicated code here. It's going to look a little bit complicated at least, but then I'm going to explain what it's doing. So this is what this backprop function for the result of an addition operation is going to look like. So yeah, it looks a little bit complicated, but basically what all this is saying is, okay, these are the instructions for what to do when the input to backprop is a value of this type parameter, where the function type of this operation is a subtype of addition or plus. So just to review a little bit of this, let's go back to our like classic example here. So let's take a look at what type z is here. So z is type of z. Yeah, so this is the type information for z. And it looks pretty complicated, but this is just telling us that, okay, like the op type here is an addition operation, and the operands were two values of type parameter nothing, so two like leaf node values here. And the cool thing here is that we can also access this information from z.op. So if we say, if you guys remember, op is like the third field in the value in the value type. So if we just print out what z.op looks like, yeah, it tells us similar information. This is an operation object. And remember, the operation objects have two fields. There's the op, which is the actual operation, and then the args, which is the operands that we're using in that operation. And yeah, the operation here is a plus, and then the operands are the two values x and y. And then we can actually access these fields like this. So we can say print line z dot op dot op, and that should give us the plus sign. And then we can also say z dot op dot args that directs us to the operands. And the cool thing is that we can actually edit these operands using this notation like this. So if we want to, so let's take a look, for example, at like how to edit the gradient of x this way. Because remember, what we're doing with backprop is trying to update the gradients of the operands. So here we can say, like I'll print out x.grad, and then we can actually get a hold of x like this, actually. Yeah, we can actually get a hold of x, and we can even get a hold of the gradient of x like that. This is just another way of writing this, actually, because we're getting a hold of x from z by going into z.op and then looking at the first operand of that operation. And then we can actually even update the gradient of x this way. So if we say, okay, this gradient is now equal to 1, then if we print out the gradient of x again, yeah, we can see that it's now equal to 1. So we've successfully updated the gradient of x by accessing x from z.op.args. Yeah, so this is basically what we're going to need to do in our backprop function for addition. We're going to get a hold of the operands that went into making val. So, for example, if val was a plus b, what we're trying to do with this backprop function is update a.grad and b.grad. And the way we're going to get a hold of them is like this notation here. So we're going to say val.op.args. The first argument, that would be like a here, basically, dot grad, and then equals something. We're gonna somehow update it, right? And we're also going to do this a second time for the second argument. Okay, so at this point, I'm gonna give you guys the answer for how we're going to update these gradients, and it's going to look a little bit weird at first because yeah. So first of all, I'll tell you guys what seems like it should be the answer, but isn't gonna work well enough. Is that it seems like the answer should just be setting both of them to 1, right? Because in our simple example, like x plus y equals z, the derivative of z with respect to x is 1, and the derivative of z with respect to y is 1. So it seems like we should just be setting both of these equal to 1, right? But no, that's actually not going to cut it for us in every case, because some cases we want it to handle are going to be a little bit more complicated. So what we actually need to do is we actually need to not set it like this at all, but actually increment it, and we're going to increment it by val.grad. And yeah, this is going to seem a bit strange at first because I know it looks a little bit more complicated than maybe we were expecting. But yeah, we're gonna actually be incrementing both of those by val.grad. So first of all, let's talk about why this works for our simple case. So in our simple case, when we're doing just x plus y equals z, we're going to be doing something like, okay, somehow in our user-facing backward function, part of what this is going to do is actually like one of the first things this backward will do is going to be set the gradient of whatever our last resulting variable is. That gradient will automatically be set to 1. Because the gradient of any variable with respect to itself is always 1. So this is basically just saying, okay, we're going to set this in our backward function. That's just saying like dz equals 1. And then, okay, so then internally, this is going to call backprop of z. And what this backprop z function is going to do is it's going to say, it's basically going to say z.op.args1 grad plus equals whatever the gradient of z is, which is 1. So then this is going to be going this is going to say x dot grad is incremented by 1 basically. So x dot grad will be going from 0 to 1. And then same thing for y, right? So this will actually take care of our simple case like that. But the reason we're writing it in this complicated looking way is that we want it to eventually be able to handle like more difficult cases. So I'm going to show you guys like a more difficult case that we want it to also be able to handle. So what if we had just said, rather than stopping at z, what if we had just said, okay, we have x equals 2, y equals 3, z equals x plus y, and then we said w equals z plus x. So we're using x a second time, and then we're calling backward on w. Then when we do this, we should have x dot grad equaling 2, because we've used x twice. So at this point, the derivative of w with respect to x is actually going to be 2, because we've used x twice in this thing. So that's why we're incrementing. We don't want to just set x dot grad equal to 1. We want to increment x dot grad by 1 every time we see x. Every time we have to update x for an addition operation, we want to increment it by 1, basically. So that's why we're incrementing rather than just setting. Yeah, because when we're doing it like this, again, backward is like the user-facing full backward pass. This is going to be calling backprop on w first, and then it's also going to call backprop on z, and both of these will be updating x.grad. So we want both of these to increment x.grad by 1, so that we're ending up with x.grad equals 2. And of course, this is also going to be, we're also going to be calling backprop on x and y, but since those are these like leaf nodes, these are just going to do nothing, right? But yeah, that's why we're incrementing. And then, okay, the second question is, why are we incrementing by val.grad rather than just incrementing by 1? So in the simple case with addition, it's just 1s all the way back. If we were making a package to only deal with addition forward and backward passes, then it would actually be okay to just increment everything by 1. But we're setting this up in a way that this is going to allow us to eventually use the chain rule for like more complicated operations. So yeah, we're basically thinking ahead here about the chain rule. So let's say that like we have again our simple example, and you know, maybe I'll try to comment some of this stuff so there'll be like kind of notes for you guys. Like y incrementing rather than setting, and then y incrementing by val.grad rather than 1. So let's say we have again our simple example like this, but let's say that yeah, so far we've always been considering like the result of our addition operations to be like our final output that we want to calculate the like all of the derivatives for. But let's say, thinking ahead, thinking when we eventually build out this package, let's say that Z was actually not, let's say that Z was actually not like the final result. Let's say that Z itself was like another intermediate step where we eventually had some final loss function where the loss function was just like 6 times Z or something. So at this point, if we're doing like a backward, sorry, I'll make this say comment backward pass on the final loss number. So this is going to first calculate the derivative of the loss with respect to Z, and that's actually going to be 6, right? Because the derivative of the loss with respect to Z is 6, meaning that increasing Z by 1 increases the loss by 6. And this also means that Z dot grad is going to be 6, just for this example. And then when we eventually keep going back for this full backward pass to calculate x dot grad and y dot grad, so in this case, x dot grad isn't the derivative of Z with respect to x, it's the derivative of the final loss with respect to x, because that's what the full backward pass means, is that we're calculating the derivative of the final resulting number we end up with respect to all of the inputs at all of the different levels. So I'll just say, like, this is not dz dx, this is d loss dx. And so that's why we're using z, like z dot grad. We're incrementing by z dot grad, is because we don't want x dot grad to equal 1. So it's not x dot grad. It doesn't equal 1 because that's what the derivative of Z with respect to X would be. But the derivative of the final loss with respect to X is, if you guys remember the chain rule, it's d loss dx equals d loss dz times dz dx. Yeah, so that's the chain rule, and so we can just plug in some numbers here. So d loss dx equals, we already know that this is the gradient of z. So yeah, this is the gradient of z. So this is z dot grad, which is equal to 6 times dz dx, and then that gives us 6 times 1 equals 6. So if any of that is confusing, you guys may even want to like work this out on paper to like prove it to yourselves. But yeah, this is the explanation of why we're incrementing by val.grad here rather than just by 1, is because val might not be the final variable that we're calculating the derivatives of. Val might be another like intermediate step where val has its own grad with respect to some final number. So if that's the case, if val is like an intermediate step, then we want to calculate, we want to basically chain rule everything back through all the steps. So that's why we're using val.grad rather than incrementing by 1. So yeah, if any of that's confusing to you guys may want to actually like prove it to yourself out on paper why incrementing by the val.grad allows us to use the chain rule when it comes to these addition operations. Okay, I know that was a lot for you guys, but I promise this is like the hard part. So if you guys are successfully understanding like this stuff, this is the hard part for all of this whole video series. After you like comprehend this about how to do like the backward pass for addition successfully, Everything else from here is going to be like pretty easy, even when we get to tensors and stuff. I know we haven't even started talking about tensors yet, but yeah, that's why I'm explaining everything with values, because it's like a little bit easier to understand conceptually. But yeah, this is the hard part. So yeah, I think that's probably enough for this video, because I've kind of given you guys a lot of complicated stuff to kind of wrap your head around, just about this function right here. So I think we'll just say that that's good for this video. And then in the next video, we're going to be talking about how to actually write this backward function. So if you guys remember, this backprop is like an internal function where we're going to be calling backprop for all of the different variables. But this backward function is the user-facing function to call the full backward pass. So yeah, I think we'll save that for the next video. And yeah, next video we'll talk about how to write this function for the full backward pass. Yeah. Okay, so thanks for watching. The code will be up on my GitHub if you guys want to check it out. And yeah, thanks for watching, and I'll see you guys next time.